Welcome to my channel Phi Concepts CHF. In this video, we are going to see about the experiment of surface tension, where we will see the aim, the apparatus, formula, theory, diagram, procedure, observation table, calculation, result. Aim: to determine the surface tension of the given liquid by capillary rise method. Apparatus: we will require a capillary tube, a pointer clamped in a stand, traveling microscope, clean water, beaker. Formula: P is equal to RH rho g upon 2 cos theta, where the value of g, it is acceleration due to gravity. G is equal to 980 centimeters per second square. R is the radius of the capillary bore. H is the height of the liquid column in the capillary tube. Theta is the angle of contact of the liquid, and rho is the density of the liquid. We are going to take water as liquid. So for pure water, the angle of contact theta is equal to 0 degrees, and the density of water rho is 1 grams per cc. So if you substitute these values in this formula will become T is equal to RHg upon 2. Theory: surface tension is the ability of a liquid to stay in its fixed shape. It is the property of a liquid by virtue of which its free surface at rest behaves like an elastic skin or a stretched rubber membrane with a tendency to contract so as to occupy a minimum surface area. We denote it by the symbol T or by capital S. Its SI unit is newtons per meter. CGS unit is dyne per centimeter. There are certain forces appearing in the liquid. One force is the cohesive force. It occurs between the same type of molecules attracting each other. Because the water molecules attract each other, this significantly affects the shape of the water structures. Then another force is the adhesive force, which occurs when the molecules of different types are attracted together, like the adhesive force occurring between water and the glass. As the charged particles of water are attracted to the glass more than they are to each other. The surface tension arises due to the cohesive interactions between the molecules in the liquid. At the bulk of the liquid, the molecules have neighboring molecules on each side, like it is shown for this molecule. It is attracted to the neighboring molecules from all the sides. Molecules are pulling each other equally in all directions, causing a net force of 0. However, at the surface, the liquid molecules have only half of the neighboring liquid molecules compared to the bulk of the liquid. Like if you see for this molecule on the surface, there are no molecules on the top. There are molecules on the sides or below it. This makes the molecule associate more strongly with the molecules at its sides and causes a net inward force towards the liquid. This inward net force causes the molecules on the surface to contract and to resist being stretched or broken. Hence, the surface is under tension, which is why the name surface tension comes. This force resists the breakage of the surface and it is called as surface tension. The stronger the cohesive force, the stronger the surface tension. Besides the cohesive force, adhesive forces also exist. They cause water molecules to try to stick to the solid surface. The most common example of the effect of adhesive force is the meniscus, which you can see here or here. The convex or the concave upper surface of a column of liquid, the curvature of which is caused by the surface tension, is called as the meniscus. The water molecules respond to an attractive adhesive force pulling them towards the glass walls. Like near the walls of the capillary tube, the adhesive force pulling the water towards the glass walls is stronger than the cohesive force pulling the water molecules together. So the adhesive force is more compared to the cohesive force in water. This attractive force, that is the adhesive force, it pulls the water up the sides of the glass tube against the downwards pull of gravity. Now, that is not the case for mercury. Mercury is repelled rather than attracted to glass, as it is shown in this diagram. The mercury tries to minimize its contact with the glass walls. This causes an upward bowing of the mercury liquid against the downwards pull of gravity, as it tries to maximize the contact between the mercury atoms and minimize the contact with the glass wall. Due to the surface tension, small objects will float on the surface of a fluid as long as the object cannot break through and separate the top layer of the water molecules. When an object is on the surface of the fluid, the surface under tension will behave like an elastic membrane. Examples of surface tension. Certain insects such as the water strider, they can walk on the water because their weight is not enough to penetrate the surface. Soaps and detergents that we use, they help in the cleaning of the clothes by lowering the surface tension of the water so that it more readily soaks into the pores and the soiled areas. The strength and effectiveness of detergents are also partially determined by the surface tension. The major reason for using hot water for washing is that its surface tension is lower and it is better wetting agent. But if the detergent lowers the surface tension, the heating of water is unnecessary. You can see the example of surface tension in paints applied on the wall. What would happen if the paint spread like plain water on a wall? The surface tension is too high and you cannot get the paint to spread evenly on the wall. On the other hand, if the surface tension is too low, the paint layer will be too thin and the surface under the paint will show through. So the surface tension of the paint should be carefully maintained to produce the desired thickness without creating any uneven patches. The liquid rises in a capillary tube because of three types of forces, with adhesion, cohesion and surface tension. The interaction between the cohesive forces and the adhesive forces causes the well-known capillary action. We use the capillary method to determine the surface tension. Besides that, capillary action has many applications like cleaning the surface of a table. If water falls on the surface of the table, you can clean it with sponge. It absorbs the water. How soil absorbs rainwater, etc. So we have seen the theory of surface tension and also we saw about capillarity. Some precautions that are to be taken while doing the experiment. Capillary tubes should be perfectly vertical and fixed parallel to each other. Presence of impurities in the liquid can alter the surface tension, so cleanliness is desired. Avoid bubbles in the liquid column. Handle the glassware with extreme care. There should not be too much fluctuation of surrounding temperature. This is the diagram. We have a beaker in which we take water. In this, we immerse the capillary tube so that the water will rise in the capillary tube. There is a traveling microscope. Using the traveling microscope, we find the rise in the water in the capillary tube. This is the actual level of the water in the beaker. We can see that water has risen in the capillary tube. So this height h is to be measured using the traveling microscope. So we will clamp a pointer which is just touching the surface of the water. Using the traveling microscope, we will measure the reading of this level and also we will take the reading of the pointer which is just touching this surface of the water, and we'll take the difference of these readings which will give this value of h. We'll see the procedure. First we'll determine the least count of the traveling microscope. Then raise the traveling microscope to a suitable height, keeping its axis horizontal and towards the capillary tube as shown in the diagram. Bring the microscope in front of the capillary tube. You are able to see the horizontal and the vertical cross wires through the microscope. Make the horizontal cross wire just touch the center part of the concave meniscus. Note the reading of the front of the capillary tube, which we will denote as H1. Now we will lower the microscope so that the pointer tip becomes visible. Lower the microscope, adjust it, and make the horizontal crosswire touch the tip of the pointer and take the reading as H2. The radius of the capillary tube will be given to you. Suppose it is 0.049 centimeters. We will take the reading of H1 and H2. For H1, we will note down the main scale reading on the main scale of the microscope, and also will note down the vernier scale division. Like main scale reading here is 5.6 and the vernier scale division we get as 10. We will have to multiply it with the least count of the traveling microscope, that is 0.001, and then we will add both these to get the total reading H1. Same thing is done for the pointer. This is the reading for the meniscus. Same thing we will do for the pointer also. We will take the main scale reading and the vernier scale reading and we will add both of them and we get H2. We will take the difference of these two, H1 minus H2, we will get H, the height. Then we will substitute everything in the formula. R is given, radius of the capillary bore 0.049. H we have just got 2.608 and acceleration due to gravity, that is G, its standard value is 980 centimeter per second square. Everything is substituted and we get the surface tension value as 62.61 dynes per centimeter. We'll write down the result. The surface tension of water is 62.61 dynes per centimeter. Actual value, the standard value is 72.8 dynes per centimeter. These are some of the e-resources that you can refer. Thank you for watching this video.